Relativity.
Diana, did you ever stop to be amazed at how a GPS unit works?
Not really. I got one for my birthday once. Chaucer, did you ever use one?
No, never needed one myself. I always know where I've been, so I always know where I am. Kevin, are you going to tell us how it works?
I sure am. It's a good intro into relativity. Jeeves, want to take over?
Relativity is just a method for two people to agree on what they see if one of them is moving. And since we all move about pretty regularly, we can find many examples of how useful relativity is in everyday life, even if we don't call it by name. One miracle of modern life is the Global Positioning System, or GPS. It is pretty amazing that the GPS can pinpoint your location anywhere on Earth to within a few yards. And this magic depends entirely on the existence of 24 satellites 12,000 miles above the Earth, and a little relativity. Briefly, here's how it works. The GPS receiver gets a timing signal from several different high-flying satellites, and using Einstein's theory of relativity, it calculates the distance from each satellite. Throw in a little triangulation, and out comes your location. Simple in concept. But to do this successfully, the timing signals must be accurate to a few billionths of a second, so that the distance calculations can be accurate to a few yards. But with all this motion going on, time and distance must be reconciled carefully. Without Einstein's version of relativity, the accuracy of the global positioning system would drift more than 7 miles every day. But of course, relativity was not a new concept with Einstein. The problem of how two people reconcile their observations about the world if one of them is moving has been addressed for centuries. Let's ease our way into relativity with some common experiences. If you are traveling in a car on a smooth, straight stretch of highway, there's no sensation of motion at all.
You mean I could read a book, pour a drink, or flip a coin, and everything looks and feels the same as if the car were sitting still?
That's because relative to the car, you, the book, the drink, and the coin are not moving. Notice that this works only if the car is not changing direction or speed.
So if the car accelerates or turns, pouring that drink becomes a real problem. Oh, but constant motion feels just like sitting still.
And if you want to know what it feels like to move at 1,000 miles per hour, just look around. Because of the Earth's spin, we zip along our time zone at a speedy 1,000 miles per hour. And because of its motion around the Sun, the Earth carries us through space about 67,000 miles per hour. And because of the motion of our solar system, about the center of our galaxy, we are moving at more than 500,000 miles an hour. But it's not enough to ask, how fast am I moving? We must ask, how fast am I moving relative to some other thing? Let's make up a simple rule that allows two observers to agree on how fast something is moving. We begin at a moving walkway at the airport. The walkway is moving at a brisk 3 miles per hour. So, if Susan simply stands on the walkway, she is moving at 3 miles per hour, relative to Sarah, who is standing still but not on the walkway. If Susan walks on the walkway at 3 miles per hour, she can accurately say she is walking at 3 miles per hour. But Sarah sees her moving at 6 miles per hour. And if Susan walks against the walkway at 3 miles per hour, Susan can still say she's walking at 3 miles per hour. But now Sarah sees her as standing still, 0 miles per hour. So our first conclusion is that two observers can simply add or subtract their speed with respect to each other to any measurement of velocity they make. This idea is the basis of classical relativity. Here's another scenario. Suppose there's a truck moving down the road at a constant speed of 50 miles per hour. On the back are a baseball pitcher, a catcher, and their pitching coach, armed with a speed gun. As long as the truck doesn't speed up or slow down or hit any large bumps, they can conduct pitching practice just the same as they would on the baseball field. And when the pitcher throws a 100-mile-per-hour fastball, the coach's speed gun will read 100 miles per hour. The ball is indeed moving 100 miles per hour relative to the pitcher, the catcher, the coach, and the truck. But suppose an observer standing by the side of the road clocks the speed of that same baseball. What speed would this observer measure for the ball? Well, the ball would already be moving at 50 miles per hour when the pitcher was just holding it. So this observer would measure a speed of 150 miles per hour for the pitch, the speed of the ball relative to the truck, plus the speed of the truck relative to the observer.
This seems pretty easy. Early scientists just needed to visit an airport or play baseball on the back of a truck, and they became absolute relativists.
Yep, but not many of them took advantage of those opportunities.
Kyrie eleison.